access the OBE system since this morning lah kan. But the system cannot be accessed lah yang seperti kamu lihat dalam screen sekarang tu kan. It may be being updated or maintenance process lah, maybe lah. Saya tidak pasti, tapi dari pagi tadi saya cuba memang tidak dapat lah. So in this regards, we will record attendance later after the system return to normal lah kan. So I hope all students take note of this matter lah. Okay, untuk pagi ni. So saya teruskan untuk we continue our lecture session today. Okay, still same in the topic of soil classifications. We will cover continue to the previous lecture topics lah. Okay. Okay, boleh nampak slide kan? Alright, thank you for respond. Okay, so this topic is a continuation to the previous session, which is soil classification part 2. Okay, so before we begin, let me do a quick recap of what we have covered in the previous session on soil classification. Previously, we have introduced the basic of how soil are classified based on their physical properties, which is particularly focusing on the particle size distribution, right? We have discussed on using the SIF analysis for coarse grain soil, and also we mentioned on the sedimentation method for fine grain soil. So we also have introduced the concept of Atterberg limits as the terminology in soil lah kan, secara in brief, which are essential for classifying the fine grain soil based on their plasticity behavior. So due to previous session we only have time to cover, which is touch on the brief part lah kan. And today we will continue with a deeper look into this topic. So today's session we will explore more on the Atterberg limit in detail, including the liquid limit, plastic limit, shrinkage limit, ni lah kan, how they related to soil consistency, classification and engineering behavior lah. So the learning outcomes for this topic today, at the end of this lecture, you should be able to explain and outline the Atterberg limit test and to analyze the result obtained. So ini adalah kita punya objective for today's session lah. Okay. Okay, this slide highlight the problem statement in geotechnical engineering. So the changes in engineering behavior of soil affect civil engineering structure and human life. Okay, so the key idea from this slide is actually want to deliver that soil is not a static materials. It change its behavior with moisture content, compaction, and also the external forces lah, such as rainfall, drought, and so on. So these changes can cause the structural damage to buildings, foundation failure, soil settlement or swelling, and also landslide and erosion lah. So the illustration here shows comparison between dry and loose soil. Gambar aja sebelah kanan tu kan, dry and loose soil, which is vulnerable to erosion, instability and poor load bearing capacity lah. While wet and compacted soil, more stable but may suffer from excessive pore water pressure or swelling lah, seperti yang kamu lihat dalam gambar raja tu sebagai illustration lah. So understanding this behavior is crucial for designing the safe, resilient civil engineering structure lah. Okay, sebagai introduction saja. Okay, as I mentioned, this topic is a continuation to the previous, still in the same topic, soil classification. So before we dive into today's topic, let's quick recap lah what we have covered previously. As mentioned in our last lecture, ingat lagi kak tidak? Ingat bahkan hari Jumaat lepas. Coba. Okay. Okay, if we recap back what we have discussed in our last lecture, we discussed on the particle size analysis. We noted that the sieve, the dry sieve method, which is the sieve test lah kan, is best suited for the coarse grain soil such as gravel and sand. So this method allows us to separate particles based on size using a stack of sieve kan, yang saya telah mention lah last week lecture. So however, when dealing with the fine grained soil like silt and clay, the sieve method is no longer effective kan. So instead of in this case we use the hydrometer or sedimentation method, which measure how particles settle in water over time to determine their size distribution. So today we will continue our discussion by introducing another important method for analyzing fine grain and cohesive soil, which is Atterberg limit lah. Okay, so this limit, Atterberg limit, help us understand the behavior of soil under different moisture content, which is they are key to classify and analysis the engineering properties of soil lah. Okay. Okay, before we explore the detail of Atterberg limits, let's a brief look at the origin of the concept, the Atterberg limit lah. So the Atterberg limits were introduced by ni lah, kamu tengok di sini kan, Professor Dr. Albert Morris Atterberg, Swedish chemist and agricultural scientist who lived from 1846 to 1916. So basically Atterberg was the first to propose a particle size limit to less than 0.002 mm, which is to classify the clay particles. Okay, through his study, this professor kan, he discovered that plasticity is a unique and defining property of clay soil. So from his investigation, he developed what we now call the consistency limit. Itu yang saya ada bagi brief introduction last Friday, which are this consistency limit, which are named after him and are still widely used in geotechnical engineering today lah, yang kita gunakan sehingga kini lah. So kita akan discuss more on this today. Okay, why Atterberg limit? Why we study about Atterberg limit? Okay, so the Atterberg limit are crucial because they are the parameter helps us classify soil based on the consistency and predict the behavior in different engineering application. Okay, so for example, A particular soil might be suitable for subbase layer in road construction, while another types may be more appropriate for building foundation. So we can use this parameter in determining the suitability of the soil lah. So these limits are also help us understand how the soil behave when water is added. Okay, air yang sedikit, medium or more. So if the soil becomes too saturated, it can behave like a viscous liquid and begin to flow under its own weight, leading to issues like slope failure ataupun debris flow and so on lah. So understanding these limits helps in design lah, basically in civil engineering project lah. Okay, itu adalah introduction for Atterberg limits, why we study about Atterberg limit lah, kan? So as we increase the water content in a dry soil, its consistency changed to 4 distinct states, as you can see from this slide, kan? From solid to semi-solid, then plastic, and finally to liquid state. So dia bertukar ada dalam 4 keadaan ni, yang mana dia dipengaruhi, it is depends on the soil moisture lah. So these are known as consistency states of soil. Okay, each of these transition mark a significant change in soil behavior and engineering properties, such as their strength, stiffness, and workability. So understanding this state is crucial lah for classifying the fine grained soil like clay and predicting how they will perform under varying moisture condition. Okay, in engineering application lah. So dia penting in soil classification lah. Okay. So 4 state of consistency, as I mentioned here, when the water content of the fine grained soil is increased, it transitions through 4 consistency state, from solid to semi-solid to plastic and finally to liquid state. Inilah yang seperti yang dilihat dalam slide ni ya. Okay, so each boundary between this state is defined by a specific limit. Okay, as you can see, okay, the shrinkage limit here, which is marked in the transition from solid to semi-solid, and then the plastic limit is where the soil become plastic, and the liquid limit, tengok sudah, define the point where the soil begin to behave more like a fluid lah, kan? So this limit help us understand how soil is performed in the field, especially important for foundation lah, kan? Foundation design, embankment, slope stability assessment lah. Okay, yang mana is changed with the alteration in the moisture content ataupun water content in the soil. Okay, in this slide, the diagram shows how the soil changes state depending on the moisture content lah. As you add water, okay, wetting process, a dry soil transition from solid state to semi-solid state, then to plastic state, and finally to liquid state. Ini yang dipanggil wetting process lah, from left to right. Okay, if you dry the soil in reverse, which is from right to left, okay, the transition go to another way kan, which is each of these boundaries shrinkage limit, okay, plastic limit, liquid limit, so it marks a change in the soil consistency lah, daripada right to the left lah. So this help to understand why soil behave differently in dry and wet condition lah. Okay, kalau ada soalan tanya, if you have question you can ask. So now looks how we define the transition between the solve consistency state using a tebak limit. So ini pun saya sudah mention tadi, but then just notes here that there are 4 states divided by the tebak limits, which is the liquid limit, plastic limit, shrinkage limit. Inilah LL, PL, SL. So these limit are specific moisture content value that separate the 4 states lah, which is for liquid limit marks the boundary between liquid and plastic state, while plastic limit separate plastic and semi-solid state, and the shrinkage limit defines the transition between semi-solid and solid state. So all these LL, PL and SL are determined by water content and can be measured through laboratory tests. So penting untuk kita fahamlah semua LL, PL and SL is quantified in water content, moisture content and we can determine in lab test lah. So kita pergilah. First one is we go through how we determine the liquid limit using Casagrande apparatus. This is the procedure lah to determine the LL in the lab. There are 2 methods actually. The first one is the Casagrande apparatus ataupun Casagrande method. So saya bagi brief lah on the procedure. A salt sample is mixed with water and placed in the breast cup, as you can see in the figure, left figure. Itu adalah Casagrande apparatus. So salt sample yang kita tu mix with water kan, and then we put on the breast cup seperti yang kamu lihat dalam gambar raja ni. Sorry, saya ambil mark dulu. Ni kan, di breast cup, this is your self sample, ini kan. And then using a grooving tools, we cut a groove at the center of the soil, which is the here grooving tools, and then we make a cut kan at the center of the soil. Okay, and then the crank is turned, which is cause the cup to be rise and drop repeatedly. Inilah kita pusingkan alat ni, yang mana it will cause the cup to be rise and drop repeatedly from a standard height lah, kan? And then we count the number of blows it takes for the groove to close over a distance of 12 mm. Inilah sehingga dia menutupi alur yang berada di tengah ni. So the number of blows is takes from this value here di sini kan. So the moisture content at which this occur is recorded. So this process is repeated for different moisture content, and the result are plotted on the graph, which is semi-log graph. Number of blows versus the moisture content, and the moisture content corresponding to 25 blows is taken as the liquid limit of the soil. So this method help assess how the soil behave under different varying moisture conditions, especially important for the clay soil lah, which is considered as fine grain soil. Kan? So this is the plots that we can obtain based on the data that we gather from the lab test. So after conducting the Casagrande test and recording the water content for different number of blows, we plot the data on this graph. Okay, so x-axis represent the number of drop or blows, dia panggil blows kan, and y-axis shows the corresponding water content of the soil. Kan? Okay, so the best fit straight line is drawn through the plotted point. So we have 3 points here. So we draw the best fit straight line through these plot points, Then the liquid limit is obtained from this curve as, sorry, kan curve kan, line kan, as the water content that correspond to 25 loss. As shown here, the liquid limit is approximately 46.4%. Kan? So this apa method ensure apa to determine the Li lah, especially for clay soil, okay, ataupun fine grain cohesive soil. So example, saya bagilah example kan. To solve example 3.1, which is given the result of Casa Grande test seperti dalam table berikut, number of loss and water content. So determine the liquid limit of the soil. Okay, kita go terus sajalah. Ini adalah contoh result from the Casa Grande test. And step by step solution is, first one we need to plot the the curve lah kan, dipanggil the plots lah kan, the points that we obtain from the Casa Grande test, which the x-axis was in the we consider the log scale of normal of a number of loss, okay, number of loss x-axis, and y-axis is the water content in percentage. And then we plot the data points that given from the tables from this example. Inilah kan number of loss and water content. Plot in the graph scale, and then we draw the best fit line, straight line. Okay, read, and then from these lines we read the water content at 25 loss. Okay, from the best straight line tu kan, and we get the moisture content at 25 loss equal to 38%. Inilah liquid limit. Boleh kan? Simple saja test ni. Okay, yang mana kamu student need to know about the procedures and how to analyze the result lah. Okay. Okay, next. Macam slow sikit internet kan, sorry ya. Okay. Okay. Next, still in determining the liquid limit using the Falcon test. So Falcon test is an alternative method to the Casa Grande cup for determining the liquid limit for fine grain soil. So the procedure is as mentioned in the slide here. We prepare the mixed soil sample and place it in the penetration cup. Okay, as you can see from the slide here, ini adalah penetration cup tu lah, yang mana we will put our sample soil, mixed soil sample, and then gently lower the cone to adjust touch to the soil surface. Here we have boleh nampak ke tu? So we lower the cone, dia ada cone di sini, to adjust to touch this soil surface, and then release the cone and record the penetration depth in millimeter. So repeat the test for various water content, which is we mix our soil with different moisture content, and then we repeat the procedure, which is put the soil sample in the penetration cup, and then lower the cone again to touch the soil surface, then release the cone again to record the penetration depth in millimeter unit lah kan. Then after we get several and penetration depth, then we can plot the result lah boleh lihat dalam ni. And then the moisture content corresponding to 20 millimeter penetration is defined as the liquid limit. So this method is widely accepted and also used in British standard lah. Basically kita ada nama dia standard code for this one lah. Also for Falcon method. So again we see some examples for this test. Example 3.2, you are given a set of data from a corn penetration test on fine grained soil. Inilah kan dalam table ni, corn penetration in mm and water content in percentage. So the solution approach is we need to plot a graph water content versus corn penetration on a graph lah kan, which is we can use linear versus linear or semi-log versus or semi-log graph lah as mentioned in the previous slide kan. And then from the graph we obtain the water content at 20 mm penetration to determine the liquid limit. Okay, so inilah the data, and then we plot over the linear versus linear scale. Okay, you get this one, and then from this plots, okay, based on okay lah, as we can see that the water content corresponding to the corn penetration of 20 mm is approximately 57%. Therefore, the liquid limit for the soil is 57% lah. In this case dalam case ini. Okay. We can also plot the data on the graph with the corn penetration on the x-axis and water content on the y-axis in the semi-log scale. Yang inilah seperti kamu lihat di sini kan. Yang mana pada for the x-axis we use the semi-log scale kan di sini. From the graph we can see that the water content corresponding to the corn penetration 20 mm is the same, which is 57% lah. Okay, walaupun menggunakan scale yang berlainan dalam case ini, kita akan memperoleh nilai yang sama lah. Okay, so boleh dipertimbangkan menggunakan scale linear versus linear ataupun semi-log ni lah. Okay, tidak masalah untuk method Falcon method ni lah. Okay, ada soalan? Any question so far? Jika tidak ada, saya teruskan untuk yang seterusnya, yang mana juga masih dalam tebak limit test, yang mana kita telah explain on how to determine the LL, liquid limit parameter. Now we determine on the plastic limit lah, PL. Okay, so the plastic limit is the moisture content at which the soil just begin to be plastic and start to crumble. Okay, so in this test, a portion of moist soil, okay, a portion of moist soil is rolled by hand into a thread on a glass plate or smooth surface lah. Okay, when the soil thread can no longer be rolled smaller than 3 mm ataupun 1/8 inch lah dalam kes ni. 3 mm equivalent to 1/8 inch in diameter without crumbling. The moisture content at that point is taken as the plastic limit. So this is how plastic limit is measured lah ataupun is determined. Okay, the plastic limit is actually defined as water content, as also liquid limit kan. All these parameter LL, PL is defined as water content. So in this case, plastic limit defined as water content at which the soil change from plastic state to semi-solid state. Ni yang balik saya sudah mention juga kan. So this is the test lah procedure which in plastic limit test we conduct this procedure which to determine the moisture content for plastic limit lah. So saya repeat again how we can conduct this plastic limit test is we take a representative soil sample and thoroughly mix it with water to make it in dalam keadaan moist lah kan to mix the sample in moist condition lah, okay, moist soil dalam keadaan moist, and then we roll it into a ball kan, then flatten the ball and roll it out into a thread of 3 mm in diameter. Okay, keep rolling the thread until it crumbles. So dalam keadaan after it crumbles kan, it start to crumble, we take the sample and then measure the water content. Okay, and then we repeat the process with another portion of the soil. Okay, sebab kita kena buat beberapa trial kan, at least 3 like that lah to get average value. Okay, repeat the process with another portion of the soil samples and then maybe 3 times, and then the water content at which the thread crumbles after being rolled once, okay, is the plastic limit lah. So in this case the water content at which the thread crumbles after being rolled once represent the plastic limit. We measure the water content and determine the plastic limit lah. So how we determine the water moisture content? In this case, this is the formula used lah. Okay, formula used and we can measure it in the lab. Okay, so this explains how the calculation of moisture content of soil sample, which is essential step in both liquid limit and plastic limit test. Okay, bukan sahaja untuk liquid limit but also in plastic limit lah. We will measure the moisture content in the soil kan. So in this case, this is the basic formula used lah, equation, which is moisture content equal to wet soil minus dry soil divided by dry soil multiplied by 100. Sorry. So the value of moisture content is basically in percentage unit. Okay. The equation also can be written as inilah, moisture content equal to weight of water divided by weight of soil multiplied by 100 to get the percentage. So this value is critical in determining the Atterberg limit and soil consistency. Not only the LL lah di sini. Nanti saya betulkan di sini sikit lah, LN and PL lah. Okay, used in Atterberg limits. So Atterberg limits, we have liquid limit, plastic limit, and also shrinkage limit lah. So basically all these parameters defined as water content. Kan? Boleh saya teruskan. Next, we determine of SL. SL is shrinkage limit, one of the 3 Atterberg limits. Okay. So shrinkage limit defined as the water content at which further drying ataupun moisture loss does not cause any more volume reduction of the soil. So itu adalah definition of shrinkage limit. So the key concept dia adalah below the shrinkage limit, the volume of soil remains constant even if if more water evaporates, kan, dia tidak akan berubah dari segi volume tu sudah. So this because the soil has already reached the solid state and the pores are filled only with air. Okay, so ini adalah concept of shrinkage limit lah. So on the diagram yang kamu boleh lihat sebelah kanan tu, the x-axis adalah moisture content and y-axis represent the volume per 100 gram of dry soil. So the curve shows how the volume decrease with moisture loss until it reach a constant volume. Lihat kan? Until it reach a constant volume indicating the shrinkage limit point. So kamu boleh lihat di situ shrinkage limit point tu adalah transition between drying curve lah yang dipanggil di sini kan, from right to left. Okay, constant volume tu kamu boleh lihat di sinilah. Okay, so this is the shrinkage limit, the transition between this apa nama dia ni, steep, bukan steep lah, inilah kan, this line to this constant line lah kan. So itu adalah curve show the volume decrease with moisture loss until it reach the constant volume. Okay. Then we go to the procedure. Okay. Test procedure for determine the shrinkage limit and the formula used to calculate the shrinkage limit lah. So the procedure, it begin with the preparation of the soil samples. So wet the soil sample thoroughly kan, then place in a dish coated with a petroleum jelly. Kita gunakan petroleum jelly. So divide into the 3 parts. Okay, kita punya sample tadi divide into 3 parts, and then we wet kan, kita timbang dia. So allow it to dry usually in the oven and wet again. Itu adalah basic procedure to prepare the soil sample lah. And then in terms of volume measurement, once dried, remove the soil pad and then fill the void left in the dish with mercury to determine the volume of the dry soil pad, and then lastly determine the initial wet volume, and then and the mass of the dry soil lah. Okay, so the formula for shrinkage limit is as you can see in the slide, SL equal to W is the water content of wet soil minus 100, and then multiply inilah volume of wet soil minus volume of oven dry soil pad divide by multiply by density of water and divide by mass of oven dry soil pad. Inilah kamu we can use this formula to calculate the shrinkage limit lah, based on the test conducted at the lab lah. So ini adalah basic test that we can use to determine the shrinkage limit. So note that this test is commonly used in routine practice, but they're less commonly used, but it is important for understanding the volume change behavior of clay soil lah. Dia boleh digunakan dalam ialah penentuan inilah yang dipanggil volume change behavior. Okay, basically in clay soil. Okay, ini adalah lab sheet yang boleh dirujuk lah. You can refer to this one in order to at the lab kan, to fill up the space kan, trial 1, 2, 3 and so on, to calculate the shrinkage limit lah, parameter. Okay. Okay, this slide present the analysis of Atterberg limit using Casagrande plastic chart, okay, which is a key tools for soil classification. Okay, so basically plastic index we can calculate based on value of liquid limit and plastic limit. So this LL and PL parameter can be determined based on laboratory test yang as mentioned in the previous slide lah kan. So PI can be calculated, which is plastic index equal to liquid limit minus plastic limit. Okay, we can use the value that we obtained tu kan to calculate the plastic index lah. Okay, so based on Casagrande plasticity chart, so yang kamu boleh lihat in the left side, the chart plot plasticity index PI on the vertical axis, which is y axis, and the liquid limit on the horizontal axis, x axis kan. So we can use this plasticity chart to classify the fine grain soil into categories. Okay, seperti yang kamu lihat, as you can see in the figure, dia ada symbol of Cl, Ch, Ml, Mh, Ol, OH, then Cl minus Ml. So this symbol dia ada maksud dia yang tersendiri lah. Contohnya seperti Cl is represent the low plasticity clay. Ch present the highly plasticity clay. H2 dia represent high plasticity, and Ml dia describe as low plasticity silt. Ialah M sebagai silt, L sebagai low plasticity ya. Mh, M adalah silt, H adalah high plasticity. Okay, dan Ol adalah represent organic silt kan, organic silt. OH adalah organic clay. Okay, organic clay meaning that high plasticity organic clay lah, gitu kan. While Cl minus Ml yang kamu boleh lihat di sini juga, ni kan, dia ada borderline lah between silty and clay. Silty adalah simbol M kan, C adalah simbol untuk clay. So dia adalah borderline between silty and clay, which is L represent the low plasticity behavior of soil lah. Okay, so ini adalah kegunaan plasticity chart ni lah, yang mana digunakan dalam Atterberg limit, analysis of Atterberg limit. Okay, kalau ada soalan kamu tanya, saya teruskan saja. So this slide further explain the plasticity chart, which is emphasizing how Atterberg limit help classify fine grain soil based on the plasticity index. Okay, and liquid limit lah. So ini yang saya mention tadi ni ya. C represent clay, M represent silt. Okay, and then the A-line yang kamu lihat di sini kan, ni A-line ni lah kan, is a reference boundary that separate clay from silt on the chart kan. Kalau kamu lihat A-line ni, dia kalau above or on the A-line, on the A-line, the soil is classified as clay. Below the A-line, bawah ni kan, soil is classified as silt kan. Kalau kamu lihat, M tu represent silt, M represent silt kan. So other than that, cross hatch region macam ni lah kan, cross hatch region such as Cl, Ml tu, dia adalah dual classification kan, dual classification, which is dia ada boundary between clay and silt tadi tu kan, clay clay and silty lah. So this analysis support the soil identification in USCS system. USCS means the Unified Soil Classification System. So it is crucial for choosing appropriate soil type in construction and infrastructure project lah, which we can refer to this chart in classifying our soil, especially for fine grain soil, which is consists of silt and clay type. Okay, so ini adalah kegunaan dia lah. Saya harap saya telah sampaikan yang perlu lah. Okay, berdasarkan kepada slide tadi. So we continue on this slide, which is explained on the use of B line tadi A-line kan, yang mana separate between clear and silt kan. While B-line here, as you can see here, ini kan, B-line in the middle of the plasticity chart is determine the compressibility of the fine grain soil. So what is the B line is, the B line is drawn vertical, inilah kamu tengok ni kan, vertically at LL equal to 50%, ni kan. LL is the liquid limit in x-axis, 50% represent the B line lah. So it's divide highly compressible soil and low compressibility soil. Okay, so right at the right lah kan, maksudnya right or on the B line, okay, which is LL less than 50%, soil is highly compressible, which is denote as H lah, which is highly high plasticity, which is highly compressible lah di sini ya. Which is di sinilah maksud saya right side lah kan, which is right side, which is liquid limit more than 50%. Okay, more than 50%, the soil is described as highly compressible, which is also we can see the symbol is H. Di situ the secondary letter is H, represent the high plasticity jugalah. Okay, mana high plasticity represent high compressibility of soil. While left of the B line, which is less than 50% liquid limit, di sini kan, the soil is considered low compressibility. Okay, denote with L as the secondary letter, ini kan L. Also low plasticity lah kan, di situ juga indicate as low compressibility level lah. So together this line help classify the fine grain soil under USCS system, Unified Soil Classification System, ensuring the proper soil identification for geotechnical application lah kan. So this is the example lah. We can classify the soil according to LL and PL value, where we can calculate the plasticity index based on the PL and LL value. Here the plasticity index is calculate based on the basic formula, which is PI equal to LL minus PL. Okay, the LL value is always larger than PL. In this case, the plasticity index for 3.1 equal to 38 minus 28 equal to 10 kan. And then 57 minus 25 equal to 32. So based on this value, plasticity index and LL, we can classify the soil here using the plasticity chart di sini kan. Based on the value, kita plot lah, dapatkan the symbol of the symbol ataupun the soil type lah kan, based on the value of plasticity index and liquid index. Ini kamu boleh try sendirilah. Okay, refer to this value 10 and 38, then you can get the soil classification. Okay, for this two example lah. Okay, then I continue with the next parameter, which is liquid index. So this slide explain the liquidity index Li, which is a key parameter used in geotechnical engineering also to evaluate the consistency and strength of fine grain soil based on the Atterberg limits. Okay, this is still under Atterberg limits kan. So this is the basic formula. LL equal to W is the natural moisture content minus PL is the plastic limit divided by LL liquid limit minus plastic limit. So the value of Li, which is the liquidity index, okay, can be used to describe the soil strength lah. As you can see here, Kan di sini kamu boleh tengok, which is Li less than 0 indicate the semi-solid state, which is high strength, brittle, sudden fracture is expected, while Li is in the range of 0 to 1, it is in plastic state, which is intermediate strength, which is all deform like a plastic material, and then Li more than 1, it is in liquid state, describe low strength, and solid deform like a viscous state lah. So the value of Li um, apa can be used to interpret the strength ataupun the behavior of the soil lah in terms of strength. Okay, ini adalah the use of Li value lah. Okay, saya teruskan sikit lagi ya. Harap boleh habis dalam 5 minit lah. Sorry, saya ambil masa tambahan 5 minit. Okay, so this slide represent the activity of soil, a parameter used to assess the behavior of fine grained soil also. It's especially for clay based on the plasticity index and the clay content. So basically the formula for to calculate the activity, which is symbol A, equal to PI, which is plastic index divided by the percentage of clay. Itu sahaja dia punya formula, basic sahaja kan. So the activity value, from the activity value that we calculate, it's reflect how the reactivity of soil with water lah, which high activity means more volume change. So it's used to identify the dominant clay mineral in soil sample. Okay, so as you can see from the tables in the right, kan, kamu boleh lihat di situ interpretation of activity A, kan, di situ nilai dia such as apa di situ mineral tu kan, muscovite, the activity equal to 0.25. Kaolinite is the mineral in clay, type of minerals clay, which is the activity is 0.4. Inilah, and then elite, then montmorillonite. This is a mineral that basically dominant in clay lah. Okay, so dalam kes ini it is used to identify the dominant clay minerals in the soil sample lah based on the A value kan. Okay, activity value. So the implication, high activity clay swell or shrink considerable as problematic for foundation lah di sini kan. So activity testing aids in soil classification and predicting the engineering behavior lah. As clay, we know that clay is sometimes basically considered as problematic in terms of behavior, the behavior of soil in terms of varying moisture content lah kan. We have different behavior while presents more water and so on lah di situ dalam kes ni lah. So example for this one, kamu boleh go through nanti lah kan. So given LL, PL and clay content, classify the soil according to this, calculate the activity of the soil and determining the liquidity index of the soil when its natural moisture content is 29%. So this one you can calculate based using the basic formula that I shown in the previous slide lah. Okay, so this is the answer for this one. Now just calculate and then you can get the value. Then from the value you can interpret the result lah, such as A equal to 1.16, what indicate that value. Also Li equal to 41%, what can we describe this value lah based on the Li kan, in terms of strength and so on. So for the conclusion to this topic, inilah kan, the fine grained soil can exist in one of four state, which is solid, semi-solid, plastic and liquid, and water is the agent that is responsible for changing the state of the soil Yalah, from this solid to liquid, and then a soil get weaker if its water content increase. Ini yang kita can refer to the curve, kan? And then LL, PL, and SL are defined on water content that cause changes of the state. Inilah kan, the PI define the range of water content for which the soil behave like plastic material, and LI give a measurement of strength indicator kan, and A, the activity gives a measures of degree of plasticity, reactivity, and possible mineral or clay types, and last one, the soil strength is apa, lowest at the fluid state and highest at the solid state. Ini yang saya katakan tadi lah. Clay behave differently with moisture content kan. Soil strength is lowest at the fluid state, higher moisture content, and highest strength at the solid state at dry condition ataupun dry state. Itu sahaja conclusion untuk hari ini. Topik hari ini. Ada soalan? Ada soalan berkaitan topik yang kita telah discuss sehingga jam 11 ni? Any question before? Okay, sebelum kita boleh tamatkanlah sesinya. Berkaitan dengan attendance, sekali lagi sekejap saya try access OBE system sekali lagi. Okay, the system still cannot be accessed. The OBE system to record our attendance today. The system cannot still problem lah, cannot be accessed. Maybe still in maintenance process, I don't know. Tidak ada notice and so on lah. So we will record the attendance later. I will let everyone know lah. And I will share the link later in our WhatsApp group for today's session lah. Okay, I hope that all students noted lah about this this morning later. Alright, thank you everyone. We can kita boleh akhiri sesi kita pada hari ini dengan ucapan terima kasih. Jumpa lagi pada sesi yang akan datang. Terima kasih semua.
Thank you, Dokter.
Thank you, Dokter.
Thank you, Dokter.
Thank you, Dokter.